Welcome back to Meteorology 101. I'm going to jump into some charts here real quick and then go over to the radar. We're going to look at some storms down in Mississippi, Louisiana, see what's going on down there. A couple of tornado warnings. We're going to see if those are justified. And first thing we always do is pull up the surface chart. So I'm going to build a surface chart first. See where our low pressure system has moved to. We had a frontal system pushing down along the Appalachians. We can still see some little bit of frontal activity right there, and then that low pressure system near the four corners just kind of still sitting there. It looks like that high pressure system to the north ridged in east of the Rockies and has ridged in pretty deep. So we'll take a look at some temperatures there. Let's throw some isotherms on here just to get an idea where our thermal advection is. Alright, so we still have a pretty tight thermal gradient. So we got the cold air advection right behind this low, wrapping around that high pressure system. So with the way these two high pressure systems are meeting right here, the subtropical high and then that polar outbreak, I would basically bring this down to a cold front to where that cold air advection kind of ends, and then just go stationary and then bring that back into that low. We kind of do want to wrap that around the leading edge of that, the high pressure system though. You want to keep those these two highs separated. You got to have some sort of frontal boundary there. So with that frontal boundary there, the warm air advection coming from the south, we got that high pressure pushing that moisture up into the Gulf states, and it's interfering with that frontal system. Now we have, we got moisture, instability, and lift. So the front is our lift. We have the ingredients for thunderstorms. So we'll see what's going on in this area down here in Mississippi, Louisiana. So like I said, there's some tornado warnings down there. We'll get to those on the radar in a minute before they all go away. So give me just a second. I'm going to throw some surface plots on here. That way we can see for ourselves where the wind shifts are, temperature changes, stuff like that, and get a good look at this frontal placement. Alright, so we can see our wind shift here. We get in Arkansas, northwesterly flow, 10 knots, and then a southerly flow over Mississippi. Northwesterly flow over northwest Louisiana, and then that shifting from the south, straight south in eastern Louisiana. So we can definitely see we got some sort of boundary there. We have a temperature of 68, temperature of 61. Not a real big jump right there, but if you go back behind that, then we drop down to 35. So there's a pretty cold air mass. We're down into the teens, single digits up in Nebraska. So we have a pretty cold air mass going through. And then as that front pushes to the east, over the next few days, that's where we're looking at getting all this icing, especially down in Arkansas, Oklahoma. There's going to be some icing down in there through Missouri up into the Ohio Valley. So depending on where that rain snow line is where depends on what we're going to be getting for freezing rain, icing, ice pellets, and maybe even some rain or snow. So we'll have to keep an eye on that. We'll maybe, see if we got time, maybe we could pull a couple soundings and get a look at those. A little early for the soundings just on precipitation types right now, because we know pretty much most of this is rain. But we can get a look at the soundings and see what, look at our mid-levels and stuff like that, so we can see how dry the atmosphere is, how moist the atmosphere is, and then get an idea of what's going to happen with this high pressure pushing through. So let's throw some fronts on here just from the computer analysis, and then they get pretty messy, so I really don't pay too much attention to them. We had a lot of troughing going on. Here's some prefrontal troughs. This is whatever, a couple different lows, cold air. We know we don't have real major cold air advection in the south right there. Our cold air advection ends up here. That's why it's probably throwing another low right there, right over Missouri, and then trying to bring it, kind of cold front around that high pressure system, just because of those temperature changes. I mean, it is pretty cold, but it's almost stationary in that point because of the wind directions. We don't have opposing wind direction, so we're not completely stationary, but that we just don't have the thermal advection. We got cold air pretty cold air. We got warmer air. So, I mean, there's just not a lot of thermal advection. The separation's there, but we just don't have the advection we need. Now, with that temperature, these temperatures interacting with each other, then you can get some severe weather from that, especially in the south. So, with all this moisture being pumped off the Gulf from the high pressure system. So, let's go look at these cells, and I'm going to clear that out real quick. Let's look at these cells and see what we got on radar. Alright, here's the latest base reflectivity. So pretty much missed all the warnings. The warnings are gone. Let's go, if we replay this. There's a tornado warning. Tornado warning. And then that goes away fairly quickly. Now, let's go ahead and look at this thing real quick. Let's get into those warning areas. See what they're looking at. So, with this warning, this is saying radar indicated rotation. So anytime they see radar indicated rotation, they have to throw out a warning. So if that's the case, we should be able to go to the base velocity. We can see some green in there, so maybe a weak indication of rotation, but any counts. So they kind of use that for, I'm going up into the upper elevations here on the radar, but they use that for any rotation at all. They're going to call it for a warning. So pretty weak. You only got a couple areas, even if that's even filled in with green, that might just be a whole, maybe a missing pixel or something like that. But for the base velocity, I'm not really seeing much there. Base reflectivity. Now what we can do is do a cross section on this. Do a little bit better than that. So I want to hit this pretty good where we are. That's not too hateful. Try to catch that shot just right. So we have a little bit of tilt in that. Nothing impressive. We do have 50 dBZs above 10,000 feet. That's criteria for severe thunderstorm. Doesn't always happen. It's a pretty straight shot on the updraft though. So radar indicated rotation is what caused that tornado warning. I'm not too impressed with this one. So I would say they never seen a tornado on the ground. Probably not even a funnel cloud. So that's pretty weak. Now we can do a volume scan on this. Alright, so there is the cell itself. And we got a little bit of tilt right through here. Nothing to really indicate a tornado. So I can change these settings. See if I can get. Here's 50 dBZ. And then that pretty much disappears. There's nothing over that. We got maybe 55. Not hitting 60 at all. Here's the cell as a whole. Go to the lower reflectivities. This thing's only going up to about 20,000 feet. So that's a pretty weak cell. I wouldn't be too concerned about that as far as a tornado. Like I said, rotation indicated by radar. The National Weather Service is going to throw out those warnings. So let them do their job. I don't see it. Let's go a couple more screens up. See if that warning changed at all. Nothing there. There's another warning right there. Don't want to do that. Let's go drag this down. Alright, we got pretty much the strongest part right there. Let's look at the pixels on this thing. I mean, there's a little bit of hooking in there. Nothing serious. I wouldn't expect anything out of that either. So Let me do a cross section. Here, let me go smooth that out. That's a real vertical updraft. Barely making it over 10,000 feet with 50 dBz. I went and our reflectivities, they're there for severe. I mean, I don't know why they just didn't go severe. I guess rotation indicated by radar. So once you see that rotation, it has to be called. I don't see the rotation though. We do a cross section on base velocity. Not there. We can do a volume scan. Here we can go look at rotation also. Here's our rotation chart. Really no rotation at all. So not seeing that one. Here's our base velocity. Let's pull. Let's just fill that in. See if anything pops up. I don't see any green in there, so. Not really seeing the rotation. Look at that as a whole. Lowest reflectivities, 25,000 feet maybe. So I'm not really impressed with that one either. So like I said, rotation indicated by radar justifies the tornado warning, but I'm not seeing it. I guarantee there's probably not a tornado seen on the ground. No, as far as the reports, this thing, if there was a tornado reported by a spotter or chaser, anybody that would be put on the screen, nothing's here. So pretty much not even a funnel cloud. Let's go look at this cell to the north. Alright, so this one shoots up to about 40,000 feet. So that's pretty impressive. Let's go drop these reflectivities. Go to higher reflectivities and see what we got at 50 dBz. We're barely even making it there, so got a little bit of a scattered area. So wouldn't really suspect any rotation. You would see some green. See, there's a little bit of green right there, that little dot. You'd see a lot more of that next to this blue if there's any real rotation in that storm. So we're just not seeing anything there either. But they don't have any warnings on that. That's a much bigger cell than that one to the south. So they're calling these supercells, but not very super when you're not shooting over 30,000 feet, especially those down there in the warning area. These right here, yeah, this one's even bigger, but let's go look at echo tops. Right there, that one definitely shooting up higher. We got 38,000 feet, 40,000. So we've seen that at 40,000 feet on the cross section on the volume scan. This one down here, 29, 30,000 feet. That's pretty much all you're getting out of that. So that's pretty weak. Let's go to the end here. We got 0.42 inches of hail, 26,000 feet in this area, and then up to about just about that 40,000 feet mark in that one. So that's your hail maker there. So half-inch hail, just under half-inch hail. That's not being considered severe. That's even severe. That's going to be 1-inch hail is going to give you a severe thunderstorm. And then obviously rotation is going to give you the tornado, but no warnings there yet. Let's open up our warnings window. We got a tornado in Mississippi. Let's go look at that one. All right, there it is right there. Severe thunderstorm in northern Alabama. Let this download. All right, let's go look at these cells. All right, tornado warning here, and this one is radar indicated rotation. do some cross sections. I see maybe a 60 dBz in there, so if I can catch that. These scans aren't 100%, so when I do that cross section, it's not cross sectioning this latest screen. So I have to try to catch it. There's a little bit right there. Let's go. I can move this around. There's our tilt. I've got some pretty good tilt to it, but I don't think there's anything to worry about on this one either, because we're pushing up to what, 30,000 feet maybe. A little bit of a tilt. Nothing on the ground. I'm just not seeing it there. So let's go do a volume scan. A little bit of a hook there. See if there's any rotation in that. Now we got rotation there, so there's your rotation indicated by radar. So they're right to call that one, but I'm probably not seeing anything on the ground either. We got rotation. You can see the green and the red. This is the base velocity on a volume scan. So we do have rotation throughout that storm. Let's get a better look at this thing. Let's go to let me get rid of that. Okay. All right, we're pulling overshooting tops, 35,000 feet. Good look at our echo tops right here. 31,000, 30,000 feet. So it does justify, the rotation justifies the tornado warning, but I wouldn't be surprised if you don't see anything there either. Let's go look at let's go back to the charts real quick. I want to see. Let me run a low-level wind shear. You can't have tornadoes without low-level wind shear. We did have a low-level jet. That's been hanging out in that area, so let's look at that. All right, let's run this script and see what we got for a low-level jet. It's going to probably look a little nasty on this chart because I didn't take that radar off the background. So our low-level jet's to the north. All this stuff to the south. I mean, we do have, it's covering on that northern Alabama. That's why you're seeing more rotation in those areas. You have that low-level jet to give that support. So it's a low-level wind shear, northern Alabama, Mississippi. So we definitely got the support for those severe thunderstorms. These severe thunderstorms down in Louisiana that went through, those were very weak. We've seen that on radar. Guaranteed nothing was on the ground. These up here, once this system start pushing through and they start issuing more warnings, we could probably actually see maybe a tornado touch ground, just based on this low-level wind shear. So let me get out of that. You can see the radar, like our frontal system. We still have that snow over the higher elevations. I'm going to recenter this map, get rid of all that radar. All right. Get this lined up a little bit. All right, we're still on the surface. Let's go to the 850 real quick. I want to see where these lows are. So we're still close pretty good over the Great Lakes region. That's a pretty strong low pressure system. We got the low over the west coast. Now these lines on over the Pacific are pretty much extrapolated. There's so little data out there. This program just kind of straightens out those lines. So we could almost close that low off too. Then we got the high pressure system to the south, all that moisture being pushed up off the Gulf. This is 5,000 feet, so if there's moisture at 5,000 feet, it will be pushed in. We do have a tight pressure gradient. There's your low level wind shear. I mean, that's with that pressure gradient at 5,000 feet, you definitely got a low level jet. Let's go put the radiosonde data on this. For 30 knots, 30, 35, 35. You need about 35 to 40 knots. Here's a 40 knot right there to have a low level jet. We do definitely got some wind shear going on here. So we do have the moisture present. You see all the black on the station plots. That's moisture present at 5,000 feet. So we're still saturated up in these areas. So as this moisture is being pushed up, you got moisture advection, warm air advection. Still isotherms on here. You got the upper low that's still closed off. Maybe an upper front because you have a pretty strong thermal advection coming out of that front. So you could pretty much put an upper front on the 5,000 foot 850 millibar chart. So then if you go back to the surface, you look at your surface fronts. Let's look at that real quick. I can throw those on here. Surface fronts over the 850. That'll give us an idea about where the surface fronts are. These aren't 100% accurate. We have to look at that surface data again. But then you pull that back to the cold air advection. It's almost vertically stacked, or maybe it's got a little bit of stacking to it, but not much. If this thing's vertically stacked like that, it's a steep front. So it's pretty much going to plow the weather, all that moisture through. So you're going to have all of your weather associated with that front's going to be at and ahead of the front, which in this case it is. If we look at that radar we had up, most of that weather was over the Appalachians, and to the east it was Mississippi, Alabama, pushed up into Tennessee, so well ahead of that front. So this cold air mass pushes through, and that cold front pushes through, with it being that steep of a slope with that strong of a high pressure system, it's just kind of plowing the moisture through and not undercutting it, and then raising that and creating all the weather behind the front. So this is an inactive cold front. That's a fast moving front. All weather is at and ahead of the front. So you can get some pretty severe weather along those ahead of that front too. So definitely keep an eye on Mississippi, northern Mississippi, Alabama, where our low level jet is, through Tennessee, Kentucky. As that front pushes through, we could definitely get some severe weather out of that. All right, let's get with 700. I'm going to try to keep this video short tonight. So now we're getting more zonal on the flow. We get, our jet stream. We do got that troughing. We had that long wave trough over the west coast, and then our jet stream pushing through. We got some pretty strong winds here. Let's go look at those balloon plots. 50 knots, 50 knots. So we got the strong winds pushing through this tight contour gradient right here. So that's pretty tight. You got upper level support. You got support for that inactive cold front. So we got, this thing is going to be, if you get a tornado pop up, you're going to have upper level support for that. Low pressure system all to the north. Let's go look up there real quick. That's just a big open area. Not a lot of data. You can see some, the rotation around that low. But that's a trough at 700 millibars. That's roughly 10,000 feet. So weak thermal advection. You guys were stronger thermal advection to the back of that. So I'd call that a major shortwave, having the thermal advection that we have at 700. So that still gives some significant upper level support for that surface low, which that surface low is pretty intense. It's closed off over the Great Lakes region. Stacking back to the colder air, we have thermal advection and a trough that gives us pretty good support there. Let's go to the 500. If we pull up a radiosonde, a SCU-T chart, we can see each station individually up through those layers. So you can still see that jet stream. See what kind of thermal advection we have here. Still there. major shortwave. We still get a pretty good thermal advection to the north. Getting some thermal ridging right here, and then we're going barotropic to the south. So all of our support is for that low pressure system to the north, and then that frontal system, you just have a major shortwave well to the west, giving that upper level support, but no support for those tornadoes, stuff like that. And this is at 18,000 feet. Let's look at the data plots real quick, see what we got for winds. So we're about 85 knots, pretty much all through that area. So we got pretty strong winds all the way down to 5,000 feet. We do have about 35, 40, 45 knots at 5,000 feet. So we do have a low level jet. So this jet stream, it's windy throughout the whole atmosphere. This is a pretty tight contour gradient. So we do have all the support we need for severe weather. And then that's why our frontal system is a fast moving front too, just because of our looking at the wind speeds. I mean, you're 50% of the 500 millibar winds. If you're 80 knots, 40 knots, that system's moving at 40 knots. Then you're 70% of the 700 millibar winds. So it's just rule of thumb, just for a quick idea of how fast the system's moving. All right, let's hit the 300 just because we want to get a good look at that jet. And that's a pretty strong jet max all the way through there. Put the heights, contour heights on here. Isotherms. Alright, so we're pretty much barotropic here. Now we do have a little bit of thermal advection to the north still. It's got that deep trough. We got that jet max, just supporting that low pressure system, that frontal system. We got all the jet support we need. So what that happens there is pretty much when you get we talked about the quadrants of the jet on the last video. If you get the upper level divergence, upper level convergence, then you got suppression and you got enhancement. So when you get upper level divergence, you get what's considered the chimney effect. So if the wind blows over the chimney, it will actually suck the air out of it. So you'll get the upper level divergence, and that will support that pressure system. And then in the quadrants of the jet stream, you have the divergence. You'll have a lower downward vertical motion, and that's a dampening effect, and that will suppress any of those thunderstorms or any of that severe weather. So, all right, I'm not going to spend too much time on that. Let's go with let's go look at the models. I think I haven't even got anything pulled up yet. Let's go. Let me get a model pulled up. Alright, I'm not seeing anything for some reason. Let's go. Alright, there we go. Alright, there's our system right now. Low pressure system over the Great Lakes region. That frontal system stretching back, and then we had the high pressure system over the Central Plains. So we got all that high pressure ridging in. Let me go to put some pressure on here. Strongest stuff based on the models over Tennessee, northern Alabama, which we've seen that we had that severe cell in Louisiana, but that didn't really turn out to be much. And this isn't even giving us any higher precip rates either. So Um, most of the strong stuff is to the north, and these kind of verify with that. So let's look pushing through that with that front, pushing out pretty quick. Like I said, it's a pretty fast moving system because of the zonal flow, the low level jet, the jet stream going all the way up, and we had that jet max. I mean, a huge jet stream all the way across the eastern United States. So that's just steering that flow right out of there, pushing that system out pretty fast. I'm going back and forth, might get a little confusing here for you, but now we're going forward. So it looks like most of the heavier rain in Tennessee, northern Alabama, got some in northern Georgia. So we hit the mountain range. Now you got that orographic lift. Now you can get some severe weather from that. We got moisture instability lift. That's what you need for thunderstorms. And then it pretty much dies out, gets on the other side of the mountains, and rains itself out, and just it's dead. Now this high pressure system ridges in. A little bit of unstable wave around that high pressure system pushing through Oklahoma, Arkansas. Now we got, with this high pressure system pushing moisture still from the Gulf, you're still picking up that moisture. And with some minor short waves going around that high, you can pick up, that'll give you the instability you need for rain, thunderstorms. Now this is going to be, with the high pressure system ridging in, we've seen the temperatures behind that. We were up in Nebraska, we were in the single digits, so we got to keep an eye on this. This is just precip, it's not a precip type. We need to go to precip type because this is most likely going to be that icing we're going to be seeing on Thursday. So let's get over to a winter chart. Alright, so there's the icing. Freezing rain, ice pellets, snow. So now we're going to be definitely want to keep an eye on this because we did see that high pressure system does support those temperatures to get that freezing weather. So Kansas looking like snow, northern Missouri snow, and then you get into the icing, freezing rain, and then the rain, and then we're getting into pushing through the Ohio Valley. Looks like a lot of that staying to the north. The Ohio Valley, the southern part of Ohio, might just get a little bit more rain than anticipated, for freezing. But there's a pretty good band right there for freezing precip. So, and then obviously over Michigan, northern Ohio, Indiana, all snow. We'd have to look at the accumulation charts to kind of get an idea of how much. These are just forecast models, so until you get until we can pull those latest soundings, you're really not knowing what you're getting. So if we pull one right here, I think we could pull a sounding. Saturated pretty much all the way up. 0 degree line. Deep warm pocket. See that warm pocket? So you can't see that. Just give me a second. Let me get readjust the screen. See what I gotta do here. Let's go. That's a little better. Not quite there. There we go. Pull it over. Alright, so here's your 0 degree temperature line right here. Let me get back over here where you guys can see it. Okay, so there's the 0 degree isotherm. We are close to freezing on the surface. Start to warm with height. This is currently. So these are, well, actually this isn't current. This is actually the forecast 18Z Friday the 25th. That's valid Friday the 25th. So we'd have a pretty good warm pocket right there. We have an inversion present, and then we have a deep warm layer, and we're saturated all the way to the upper levels. Any of this frozen precip below 0, all that's frozen, falls through this warm layer, and then it's going to start to melt, and then either refreeze or freeze on contact, or refreeze completely before it hits the ground, or partially freeze before it hits the ground, so you can get those ice pellets. What we need to do is look at the depth of this. This thing doesn't really give us the depth on these readings. So 850 is 5,000 feet. 1,000 millibars, 364 feet. That's right here. So roughly 400 to 500 feet is our freezing level. We need between 6 and 1,200 feet is going to be mixed precipitation. If that warm layer is between 6 and 1,200 feet, we have a pretty good warm layer. That thing's probably going to melt mostly all the way. And then we got about 600 feet, so that's only going to give us enough to partially freeze. So we're looking at ice pellets on the surface there. So this is Friday. That's pretty far out there. Let's see. It's Friday 03Z. That's Thursday evening. So if this stays accurate, then we're looking at ice pellets in southern Ohio. All right, let me fix the screen again. All right, so let's get back. And then that pushes out. I'm going to look at what's going on there. We got it's all high pressure. Looks like minor shortwave. Maybe a low pressure system is developing right there. What do we got? It does look like a low right in that area. Maybe some inverted troughing. So then we got that front stalls out. Let's see what that high pressure is doing. That's where you're going to look at your high pressure system. The leading edge of that air mass is your front. So what's happening with that high? It's kind of going more horizontal. And then so I would kind of stall out that front. Then you can get a low pressure system develop along that front and then push to the northeast, just like that. So I mean that doesn't make sense. So this is Next Lab forecast. These are models from College DuPage, if I'm pronouncing that right. Some things get pronounced a little weird, but anyway, these models are pretty good. You can pull up the soundings. You can hover over the values. You can see what your reflectivities are, see what your pressures are in those areas, and what your thickness is. So if you're looking at this, you're looking at 5,400 meters on the thickness. If you can see that bottom number, 5,400 is your frozen precip. So right there's your rain snow line. So the 5,400 meter line goes right through that area. So that's going to be your rain snow mix. So another pretty good intense low pressure system pushes through there, bringing some snow through the Great Lakes region, icing through the Ohio Valley, icing this high pressure. I mean, the high pressure is what's causing it to be frozen precip. So don't get that confused either. People get a little carried away with. They ask you why it's snowing. You say because of the high pressure. They start freaking out on you. The high pressure is dropping the freezing level to the level we need for snow. That's so the high pressure is the reason it's snow. The low pressure is the reason is we have precipitation. The high pressure is the reason we have what type of precipitation. So attention to detail, whatever. I pissed a lot of people off with that one. So pretty much that's it. We'll keep an eye on this next few days over into Thursday, Friday. See what happens there with the icing and stuff like that, and then so let's get back over here to some radar. I want to see if there are any more warnings. Go to my warning window. Here's one in Alabama. Let's get over to that one. So I did go tornado announced. Like I said, keep an eye on the ones in the northern Alabama. We got flash flooding, looks like, in Tennessee. Let's see, get rid of that. Way too much. Let me drag this over a little bit. Zoom in. Now we're at 64 dBZs. Now we're getting more intense. See where we're at with that low level jet. Now we're getting in that low level wind shear. You got to have low level wind shear for tornadoes. Our low level wind shear extended down to the northern Alabama, Mississippi, and that's where we are starting to see now some more intense cells. So that all makes perfect sense. It works. So let's do a volume scan on that cell. Bring these reflectivities up. I want to see what the 50 dBz or higher is doing. So we have the 60 to 65 right there. So now we can definitely have something on the ground there. I did kind of cut that off. Let me go back and change that. Like I said, with these scans, I got to go back a little bit so we can get that more centered. So there we go. Now, real quick, go to rotation. We definitely should see rotation in this one. Yeah, we do got rotation. So rotation indicated by radar. I'm sure that's the warning area. Let's pull that up real quick. And we got tornado watch remains in effect until midnight Central Standard Time for North Central and Northwestern Alabama. And this says this has been canceled. And it was rotation indicated by radar. So, all right, look at that. 2-inch hail indicated by radar. All right, let's pull that back. I mean, that one looks pretty good. So they did cancel it, but let's see. Let me get a better look at this. If I can catch that. That's pretty good right there. Now, we got 50 dBz is well above 30,000 feet, so that's a pretty intense storm right there. Like I said, once we get into that low level wind shear, you can definitely see the difference now. So any tornado that was called on this storm, I would agree with. The mother 20,000 feet, 22,000 feet, whatever the height on those were, that was pretty weak. Like I said, they got to call that because of the radar indicator rotation, but I wouldn't get too stressed over that one. Let's do a cross section on this. Try to see see the tilt on that one. That's what we're looking for right there. Definitely got that tilt, 60 dBz and higher, pushing almost up to 20,000 feet. So that's definitely a hail maker. You got hail in that storm. That's all that high reflectivity right there. Now let's look at higher elevations of the storm. That high reflectivity stay pretty close to center there, where that 2 inches. So there's a pretty vertical reflectivity. What I'd like to see is that stack over. If you look at the higher elevations here, we're about 4-degree tilt, and then we start coming down. Now you can start seeing more of the precip going to the west. So you can see how the structure of that storm is. Like I said, that's pretty intense. So that's pretty good. I like the high reflectivities of the of that hail. Like I said, 2-inch hail. They've just updated another warning. This one, radar indicator rotation. Look out for flying debris. Severe thunderstorm capable of producing a tornado was located near Rogersville, 14 miles west of Athens, moving east at 50 miles per hour. So, like I said, was that we've seen those winds about 80 knots in the upper levels. What we say, 500 millibars. So 50% of 500 millibar, we said 80 knots. We're about 85, so 42 and a half knots. So if we convert that to miles per hour, I don't have a conversion chart real quick, but that is 82.5 times 1.15, and that is 94. That's not going to be right. Let's see here. Since we are... No, that is right. 80... We say 82.5. So that's knots. So yeah, we go times 1.15, and that is 94. So this is moving at 50 miles per hour. So that's about 43 knots. So pretty close. We did cut that in half. 43 knots, 50 mile an hour. So that's pretty good. So I don't know what math I just did there, but 50 miles per hour is about 80 knots. Actually, 43 knots. So we were pretty close there on cutting that 80 knot wind at 500 millibars in half. So we did get there. So, all right, sorry if I confused on that one. That was actually pretty accurate, too, though, if you think about that one. 82 knots, 82 and a half knots. We were at 84 knots, cut that in half. So 43 knots. We're 50 miles per hour. So we're there. All right, sorry for rambling. All right, there's an update on the next screenshot. Let's do a volume scan on this one. I'm going to step back a little bit on that. A little bit further. We're starting to get a pretty good hook right there. So if you see that, right there's the hook. So we could definitely get a tornado out of this one. All right, I'm coming up on over 40 minutes. I'm gonna go ahead and call this video right now. I'm not live, so I'm not gonna sit here and chase this thing all night. All right, so I hope you learned something from the video. I want to say thanks for watching. Visit my website, meteorology101.com, and get your head in the clouds.